All right, all, this is Mr. Yeager. This is the last lecture for the year in this particular one. Um, and this is going off of the bonus activity for quantum theory. It's part of our standards in terms of looking at the idea of wave-particle duality. We look at it from very, very highly conceptual stage, as well as a couple calculations. But I'll tell you, it's pretty superficial in terms of what we are looking at. So here we go. All right. So the idea of quantum theory, all right, that came up is basically the idea that light itself has both particle and wave properties. Okay. It acts like a particle and a wave, and vice versa. Matter also has particle and wave properties. Basically, this duality is what we usually call it. All right. So in other words, all objects, including light, which is not obviously matter, all have both particle and wave properties, and that's what we're going to try to break down. Obviously, there's clear wave properties for light. There's clear particle properties for matter. But obviously, trying to identify the other one's a little bit tougher, and that's the whole idea of what quantum theory went after, okay, or still going after. So, to review, the wave properties is basically the idea that you actually create these waves through space. You send this energy through space, and it can reflect, refract, diffract, and interfere with each other. Okay, so those are your general wave properties. All right? So again, we are going to try to illustrate that there's this wave-particle duality of light and wave-particle duality of matter. So we already know light travels like a wave. That's not surprising. It travels as a transverse wave, up and down, up and down, up and down. Okay? We went over that in the wave unit. We went over that with optics as well. Okay? But light also has what are called particle properties. All right? And when we look at light as a particle, we call it a photon. A photon. Okay? And so what we basically came up with is the idea that, yes, light does move up and down, but in packets. Okay? Basically, it's this idea that there's individual packets of light approaching you, almost like these little dots. All right? With it turns out, actual space in between them in a way. All right? It's just they move so quickly that you never obviously can interpret any of the space. Within this space, the way I like to try to describe it, within this each individual particle space are all the different wave colors. So if this is white light coming at you, this is particles or photons or packets of light that carry all the different waves of color as it goes by. All right? Which is why if you happen to wear a shirt that's purple, the photon hits you, it will reflect back the purple frequencies of that color so other people can see it, while it will absorb all the other colors. So that's what we're talking about in terms of photons, these packets of light. Now, how can we try to illustrate that light travels as photons, as particles? And the best way we'd show that is through what's called the photoelectric effect. All right, the photoelectric effect. All right, which I think I have a link on the notes for this, which might not work anymore, but if you look up, obviously, any video on YouTube, just look up photoelectric effect, you can see good different examples, different illustrations of this. And I'll try to illustrate it some here too. But the idea is, when light hits matter, it will cause electrons to be released. So it's interacting with the particles of electrons. So it must be some sort of packet that hits another particle, and then basically makes it bounce off and get released. So this is used in solar cells. All right, this is obviously how we change solar energy into electrical energy. So essentially, what we have, if I draw it out some, is this is some sort of matter. We'll say it's a solar cell. Okay, and what we do is obviously we connect that to some wires. Okay, and then I'll connect it to a light bulb. There, using my old picture of a light bulb. Okay. And so what happens is when these photons come down and hit the matter, it will release these electrons, basically transfer the energy and release the electrons to make the light bulb glow. Okay? Obviously become bright. Now the thing is though, you have to hit what's called a threshold frequency. Okay? The substance itself has a threshold frequency, which is the minimum amount of frequency needed in order to eject electrons off the surface, all right? Which means purple light might be able to release electrons, but if I send red photons down, and if it's a red photon, that means it's only red frequencies of waves, okay? But if I send a red photon down, maybe no electrons are ejected. And that's because purple has a higher frequency than red. Okay? That's what we're basically talking about. The purple has a higher frequency than red. And it does. Going back to the idea of Roy G. Biv, frequency increases. Roy G. Biv, spelling Biv's name wrong. Roy G. Biv, red is the lowest frequency, purple is the highest frequency, or violet. Okay, it's the highest frequency. So we have to hit what's called this threshold frequency, this minimum frequency in order to eject the electrons. And that's because there is a formula that energy, I'll write this a little larger, energy is equal to h times frequency. In other words, it's directly related with the frequency. If I increase frequency, I increase the energy of the photon. All right. All I multiply it by is by this Planck's constant, 6.626 times 10 to the negative 34 joule hertz. All right. So this light carries energy. It carries packets of energy that can hit a surface and release electrons, and this is the photoelectric effect. All right, causing the things to be able to store electricity, create electricity, obviously convert it from another form. All right. So to practice with this energy formula, you can see I already filled it out, but I'll write it out a little bit larger. What if I had to solve for energy? Energy is equal to HF. HF. So I just plug it in, 6.626 times 10 to the negative 34th times 5.5 times 10 to the 14th. And it comes out to 3.6 times 10 to the negative 19 joules. Obviously, just be careful with your scientific notation. Now, understand, I'm not going to show another one here. This is obviously part of the bonus for you to figure it out. All right. What if I gave you the wavelength of light? What if I gave you the wavelength of the photon? You got to remember that velocity equals frequency times wavelength. If this is going the speed of light, we usually write this as c equals f times wavelength. I would give you that the speed of light is 3 times 10 to the 8th meters per second. And you can convert wavelength into frequency based on this formula. Or you can know that this is also hc over wavelength, because frequency is equal to c over wavelength. So I can plug it in that way as well in one step if I want to. So just be aware of that. Again, the main idea is just showing you that light can be a particle. It's being shown through photoelectric effect because it can interact with those electron particles and get them to be released, okay, if they have enough energy. Now, there is a conversion that you will be using a little bit just because it makes more sense instead of having to talk about joules in terms of 3.6 times 10 negative 19. All right, we have a new unit called the electron volt. This is a unit of energy. And basically it's saying 1 electron volt is 1 times 10 to the negative 19th joules. So obviously a very, 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 very small unit of energy. So I can convert that. I'm not going to really go over that too much. You can see basically divide 3.6 times 10 to the negative 19th divided by 1 times 10 to the negative 19th. And this amount of energy is 3.6 electron volts. That's a little bit more manageable of a number, a more understood number. But again, understand it's a very, very, very small unit of energy. Very, very small amount. Okay? Which you'll do in your practice. All right. So what about matter? Well, we know matter are particles. They're made up of atoms. That part's clearly understood. We know that it's related to particles. Okay? But how does matter create waves? What are the wave properties of matter? And so this is called matter waves. Okay? We actually say matter produces waves through space-time. Okay? And so all objects are actually creating a wavelength when they are moving. That's the key. All right? They only create a wave when they are moving. They must have some sort of momentum. Okay? There must be momentum involved. That's the key. And you'll see that in the formula right below. Okay? So wavelength of an object can be found with what's called de Broglie's equation. The matter wavelength is equal to h, once again Planck's constant, over mv. Well, if you recall, mv is momentum, so sometimes we write this as h over p. This is momentum. Okay? So the thing is, if the object is not moving, if v is 0, it doesn't even exist. It's an impossible equation. There is no wavelength. The idea, if again, this is tougher for you to see because obviously you're listening to me, but basically the idea is when I take a step, the space that I was filling in before fills back in and I displace other space. I push the space away. Think of me as basically walking through water. When I walk through water, I create waves through the water because I'm pushing. When I move forward, I push the water that's in my way out of the way while the water behind me fills in because that's where I was. Same thing is going with what we call space-time. And so technically as I'm walking along, you might, you're never going to feel it because you're going to see in just a moment, large objects don't create very large wavelengths at all. But the idea would be almost like everybody's in a pool in my classroom, I walk and everybody can feel me moving because I'm creating those waves. Including the idea of if I don't move, I'm not going to create any waves in the pool. Okay? So that is where we have matter waves. Again, we cannot detect the wavelengths of large objects. It has to be, what we'll see in just a moment, if we try to do a large object, a person, a car, even like a cup, okay, it will be too small to be detectable by anything that we have nowadays. We have to go down to the subatomic level to actually realize this. So electrons, protons, particles even smaller than that, we can detect their wavelength. So you can see we have this example here, okay? Basically, I'll go ahead and rewrite it out so you can see it. So wavelength is Planck's constant over mass times velocity. What is the wavelength of a person going 5 meters per second? That's pretty good. I mean, that's that's basically sprinting. They are creating waves through space while they're sprinting, but you can see mainly because of Planck's constant being 10 to the negative 34, 79.5 times 5 is just not going to do it. Okay, 1.67 times 10 to the negative 36. Okay, it actually gets even smaller. Okay, so meters. So that's a ridiculously small wavelength. It doesn't, again, makes no sense. It's so small that it's not going to be detected. Those waves are so close together. Okay, so very, very tiny. But if we use an atomic particle like an electron, which has a mass of 10 to the negative 31st and goes the speed of light, what you can see, I'm not going to redo this calculation, is you get an answer of 2.42 times 10 to the negative 12, which is still ridiculously small, but is something that we can actually measure with very, very sensitive equipment. This is what particle accelerators use to measure new particles. So when we discovered the Higgs boson a few years ago, this is what we were trying to detect, their wavelength. Okay? Something that showed that there's some new substance creating this wavelength because objects will create their own wavelength based on their mass. All right? You eliminate all the other ones and you can see basically what is still there. All right? So it only works well still, very, very, very small wavelengths, but they are detectable by very sensitive equipment. All right? So, to study this idea of particles having wave-particle nature, basically the particle's wave-particle nature, sorry, that's kind of a mouthful. We are interested in identifying where the particle is and how it's moving. Okay? So basically, the idea we're talking about here, guys, is if I know where it is, I can identify the particle nature of it. If I know where it is, because I can talk about it, I can feel it, I can see it, it's a particle, okay? If I know exactly where it is, in order to figure out the wave properties, it needs to be moving. Well, we have a problem here. We have a big, big problem. How can I know exactly where it is if it's moving? If it's moving, it's constantly changing its position. We don't know exactly where it is. Vice versa, if I know exactly where it is, it's not moving. So we have a problem. All right? The more I know, the more you know the location of the object, the less you, sorry, I'm trying to make it, less you know about the motion. So it's impossible to know both of these precisely at the exact same time. We can estimate, we can have some error with both measurements and get a good idea, but that's the problem, is there's always error. And so that's where we come up with this, where we have this Heisenberg uncertainty principle. He says it is impossible to precisely measure both position and momentum at the same time. It is impossible. Okay? When I have that electron rotating around, not rotating, but moving around the atom, okay? You can sit there and be like, I know that electron has wave properties and that proton has particle properties. If I want to study the particle properties, that means I have to basically slow it down and know exactly where it is. The problem is, the more I slow it down, the less it acts like a wave. And so now I have no idea what type of wave properties it has. But then if I let it move, I can figure out the wave properties, but then the problem is, I don't know exactly where it is. Is it a particle? That's basically, what type of particle properties does it have? So that is the Heisenberg uncertainty principle. All right? Basically saying there's a limit to how accurately we can figure out both the position and momentum at the exact same time. All right? That is an issue. So, you should watch the Dr. Quantum video on the double slit experiment. All right, because this is where a lot of these quantum ideas were developed, where you're sitting there going, you're shooting these electrons through two slits. All right, at one time they seem like they should be particles, but then they produce wave patterns. How can an electron produce a wave pattern? It's, that means it must have wave properties. But the problem is, and this is where everybody gets confused on that video, is if you try to focus which slit the object goes through. All right, so in the double slit experiment, what happens is that electron goes through, and as it says in the video, it goes through both, it goes through one, it goes through the other, and it doesn't go through any. It's just mind-boggling almost. How does that happen? All right. So the problem is, obviously at the very end, they try to focus. They say they put a little measuring device right at one of the two slits. Well, what are you doing there? What happens is you are trying to exactly locate where the particle is, which means what are you giving up? The movement. And that's why when they did that, it acted like a particle. It created a particle pattern based on the measurements that they have, based on the measurements. All right? And so that's basically kind of the strange idea. The more you know on one side, the less you know on the other. How do you try to balance both of these things? And that is for the later time, obviously at a higher order. All right? So that is basically the quantum ideas involved with the bonus. So go ahead and give it a try, and good luck.